So this is the first lecture about the S block elements. Let's have a look into it. The first statement. The first element of alkali and alkaline earth metals differs in many respects from other members of the group. So this is what it is important, that the first element of alkali metals and alkaline earth metals differ in many respects from other members of the group. This is what, my dear student, it is known as the second period anomaly. Second period anomaly. So, if you look into the elements which are there in the group number 1, 2, and then group number 13 to 17, if you look into them, they have their first element, they have their first element falling into second period. All these groups have their first element falls into the second period, and that is why these second period elements, they are different from the other. These elements are different from the other elements of the same group, and this is what it is observed always. And that is why, my dear students, we can say that we have this elements um, falling into the second period. They are not similar with the element of the same group, and that is what it is known as the second period anomaly. Now let's move and understand about the S block elements in details. S block elements of the periodic table are those elements which the last electron enters to the outermost s orbital. So these are the elements in which the last element or the last filled electron goes or enters into the s orbital, and that is why they are known as the s block element. As s orbital accommodate only two electrons, two group belong to the s block. That is your group number 1, which is alkali metals, and group number 2, which is alkaline earth metal. Group 1 elements, if you look into. So group 1 has got lithium, sodium, potassium, rubidium, cesium, and francium. And these are correctly known as the alkali metals. Now, why are they called alkali metals? Let us see. These elements are called alkali metals because when they react with water, they produce hydroxide, which are strongly alkaline in nature, and so they are called the alkali metals. So this is how we can say that they are called the alkali metals. Now we have the next one, group 2 elements. So group 2 has got beryllium, magnesium, calcium, strontium, barium, radium. These are commonly known as alkaline earth metals because oxides of these metals, except beryllium, are found into the earth's crust. Now please remember that the oxides of beryllium also found into the earth's crust, but beryllium does not resemble with these elements in some or the other way. But before that, before we understand about beryllium, let us see what is earth's crust. A thin rocky layer of the earth is known as the earth's crust. The hydroxide of group 2 elements and oxides of group 2 elements are alkaline. Alkaline means basic, my dear students, basic in nature. One more meaning you can understand that alkaline means something that is water soluble and basic in nature. So basic in nature and water soluble, these two are the characteristics that we can associate with the word alkaline. But oxides of beryllium and hydroxides of beryllium are amphoteric in nature. So please remember that oxides and hydroxides of beryllium are amphoteric in nature, and this is how beryllium is not similar to the other elements, or that is why we cannot, or that is why sometimes this beryllium is not considered as an alkaline earth metal, but still it belongs to the same group and it is studied as an alkaline earth metal. But the special characteristics that the oxides and hydroxides should be basic in nature, but the oxides and hydroxides of beryllium are amphoteric in nature. So beryllium is not called the alkaline earth metal because oxides of beryllium, but oxides of beryllium are found into the Earth's crust. Now abundance. How much and where are they found? So these alkali metals, among alkali metals, sodium and potassium are abundant. Lithium, rubidium, and cesium have much lower abundance. Francium is highly radioactive. The longest lived isotope 223 francium has half-life of only 21 minutes. So this is how we understand about the half-life of the elements. Alkaline earth metals. So let's study about the alkaline earth metals. Calcium, abundance of the alkaline earth metals. Calcium rank fifth. So calcium is the fifth highest element in abundance available. Then we have magnesium that ranks sixth in the abundance in the Earth's crust. Then, my dear students, we have strontium and barium have much lower abundance. So strontium and barium have much lower abundance. Beryllium is rare element, whereas radium is rarest among all the elements of group 2, comprising only 10 to the power minus 10% of the igneous rank. So this is how, my dear students, we can understand about the abundance. Now let us study about the electronic configuration. So first we should study about the electronic configuration of the alkali metals. The general electronic configuration of the alkali metals, we can write it as a noble gas NS1. We can even write about the alkaline earth metals general electronic configuration as noble gas NS2. First element of both the groups, that is lithium in group 1 and beryllium in group 2, are different from the other elements of their own group in many sense, and that is what it is known as the anomalous behavior of period 2 elements. Both lithium and beryllium belongs to the period 2, and that is why they are not similar to the other elements of the same group. Let's move and understand about the diagonal relationship. Both lithium and beryllium of group 1 and group 2 are similar to the second element of the next group. For example, let us study about the diagonal relationship. Lithium, that belong to group number 1, is similar to magnesium, that is group number 2. Beryllium, that belong to group number 2, is similar to aluminum, that is group number 13. So you can see that if you write the groups 1, 2, and 13, and then we write their elements lithium, sodium, magnesium, beryllium, magnesium, and boron, aluminum, then we can see that lithium is very similar to the magnesium. Beryllium is very similar to the aluminum. Now, why does it happen? So, you should think it this way, my dear students, that if you go left to right in a period, the atomic radii decreases. If you go down the group, the atomic radii increases. But if you go diagonally, what happens? The atomic radii remains almost same. And as the atomic radii remains same, their behavior is also very similar to each other. And that is why, my dear students, this relationship, we consider it as a diagonal relationship. And due to this, the atomic radii of lithium and magnesium or beryllium and aluminum are very similar, and that is why they show the similar properties. Similarity of lithium with magnesium and beryllium with aluminum is due to the similarity uh, ionic size is due to the similarity in ionic size as well as similarity in charge is to radius ratio. So there are two reasons why they are similar. One, they are similar because they have almost same ionic charges, ionic radii, and they almost have the same charge is to radius ratio of these elements, and that is why they are very similar to each other. Now let us understand. Now let us start studying about group 1 elements. So let us first look into the group 1 electronic configuration. We have lithium, helium 2s1, sodium neon 3s1, potassium argon 4s1, rubidium krypton 5s1, cesium xenon 6s1, and francium radon 7s1. So general electronic configuration, we can write it as a noble gas and ns1. So this is how we study about the. Then next one, the loosely held s electron in the outermost valence shell of these elements makes elements of this group most electropositive metals. So these elements, they have ns1 electronic configuration. This electron is loosely packed and can be easily removed by providing a very small amount of energy, and that is why these elements or the alkali elements are considered to be the most electronegative element among all of them. Alkali metals readily lose one electron and make M plus 1 ion, and thus they are not found in free states. So they are highly reactive, they can easily remove their electron, and that is why they are always found into the combined state. None of the element from this group is available in the free state into the atmosphere or into the Earth's crust. My dear students, you would be amazed to know that when the elements like potassium and cesium, when even the sunlight falls on them, they lose their electron and they make the positive ion. So this is how, my dear students, we understand about how easily they can lose their electron, and that is why these elements are used to make or are utilized to make the photoelectric cell or photovoltaic cell, which are used into the solar panels or solar cells. Now let us study about the atomic and ionic radii. The alkali metals have the largest sizes in a particular period of the periodic table. Monovalent M plus ion are smaller than the parent atoms. So please remember that whenever there is a positive ion formed, it has got the smaller size than the parent atom, and that is why here also, here in this group elements, when we consider, we find that the monovalent M plus ion is smaller in size. In group going down, the atomic and ionic radii increases. So we are well aware that going down the group, atomic and ionic radii increases because the new subshells are being added, and that is why the size increases. Then, my dear students, we want to study about the ionization enthalpy. The ionization enthalpy of the alkali metals are considerably low and decreases down the group. Now, my dear students, you can see that if you go down the group, the electron field away from the nucleus. As the electron is filled away from the nucleus, what happens? The effective nuclear charge decreases, and that is why the last filled electron is loosely packed, and that can be easily removed as you go down the group, and that is why the amount of energy required to remove the electron from its isolated gaseous atom decreases, and that is why the ionization enthalpy also decreases down the group. This is because the effect of increasing size outweighed the increasing nuclear charge, and the outermost electron is very well screened from the nuclear charge, and that is why it can be easily lost, and that is why the energy decreases. Now, my dear students, let's move forward and study about the hydration enthalpy. This is a very important point according to the exam point view as well as for the better understanding of these elements. The hydration enthalpies of alkali metal ions decreases with increase in the ionic sizes. So as the ionic sizes increases, my dear students, the hydration enthalpy decreases, and that is why lithium plus 1 has got the highest hydration enthalpy among all these elements. So this is how, my dear students, we study the order that lithium is greater than sodium, is greater than potassium, is greater than rubidium, is greater than cesium ions as far as the hydration enthalpy order is concerned. Lithium has maximum degree of hydration, and for this reason lithium salts are mostly hydrated. So these lithium salts are generally hydrated and they have LiCl into twice H2O. Now my dear students, we need to study about the physical properties of these elements. So let us study about the physical properties. All the alkali metals are silvery white, soft and light metals. Please remember that all the alkali metals are silvery white, soft and light metals. Because of the large size, these elements have low density which increases down the group. So as they have the large size, this density of these elements low density, and this density increases down the group. But a very important reason, many a time asked into the various exams, that why potassium is lighter than the sodium. Generally, going down the group, the density increases, but in case of potassium, the density of potassium is lower than the density of sodium. Why? The reason, because going down the group from sodium to potassium, the size increases. You can see that if you look into the electronic configuration of sodium, it is neon 3s1, potassium it is argon 4s1. So the size actually increases. As the size increases due to increase in the cell, but we know that density is equal to mass by volume. So volume increases. The increase in size outweighs the increase in mass. So you can see that the atomic mass has also been increased, and that has been increased from 23 to 39. But the increase in volume is bigger than the increase in mass, and that is why overall density decreases, and that is how we can explain that the density of potassium is lower than the density of sodium. Please remember that the density of potassium is less than the density of sodium. So mass, that is atomic mass, even increases, but increase in volume is more as compared to the increase in mass. Thus, mass is to volume ratio for sodium is more than the mass to volume ratio for potassium, and thus increase in nuclear charge due to increase in 8 protons is less effective as compared to the increase in the size due to addition of the shell forest. Density decreases, and that is how we can say that the density decreases, my dear students. This can also be understood by writing these orbitals. You can see that in sodium 3s1, 3p0 and 3d0, but all these 3p and 3d are available, and that had started from the sodium only, because if you look into the lithium has got helium 2s and 2p only. So S and P were the only orbitals possible in case of lithium. But when you go from sodium to potassium, what happens? This 3D is also added first time, and that is why uh, the difference in the volume or increase in the volume is a little bigger, and that is why the density of so increase in volume is more as compared to the increase in mass, and that is why the density overall decreases. You can see that even I have mentioned here that lithium has got only 2s and 2p. Going from lithium to sodium, 2d is not possible or available, and so increase in size and increase in nuclear charge is by 8, and thus nuclear charge overcome and decreases its size, or decrease in size is more, um, so the density increases. So my dear students, the charge in case of from going lithium to sodium, the increase in mass outweighs the increase in volume, and thus the density increases. But in case of sodium to potassium, increase in volume outweighs the increase in mass, and thus the density decreases. The melting and boiling point of alkali metals are low. Please remember that the alkali metals have generally low melting and boiling point, and this is because the alkali metals have only one valence electron that cause weak metallic bonds, and this metallic or strength of the metallic bond, please remember my dear students, that strength of the metallic bond, sorry, strength of the metallic bond is directly proportional to the number of unpaired electrons in the atom. In the atom. Atom of what? Atom of metal, because metal only show the metallic bond. So strength of the metallic bond is directly proportional to the number of unpaired electrons in the metal atom. And here you can see that they have only one unpaired electron. Remember, it is unpaired electron. So they have only one unpaired electron, and that is what it causes the weak metallic bond, and that is why these lithium, sodium, potassium, rubidium, cesium, and francium, they generally have low melting and boiling point. The alkali metals and their salts impart characteristic color to an oxidizing flame. Please remember, my dear students, that when these metals are heated into the oxidizing flame, they impart a characteristic color. This is because the heat from the flame excites the outermost orbital electron to higher energy level. When excited electron come back to the ground state, there is emission of the radiation in the visible region. My dear students, we have discussed it quite a few times, but there was an electron into the ground state, which by taking the energy from flame, this is the energy from flame, it goes to the higher energy level. So from E0 it goes to E1, and while coming back it radiates the energy in the form of coloring light or colored light, and that is why this the salt of the alkali metals, they impart the various colors. Let us see what colors these metals have, or these metals gives. Lithium gives the crimson red, sodium gives the yellow color, potassium gives the violet color, rubidium gives the red violet color, and cesium gives the blue color on the oxidizing flames. Alkali metals can therefore be detected by the respective flame test. And if any alkali metal is present into the salt, we can easily find it out by using the flame test, and can be determined by the flame photometry. So finding out, or the method of identifying the elements using the light or using the flame to understand their presence by the color that they have produced is known as the, this method is known as the flame photometry, and that is why we can detect these elements using the flame photometry, or we can detect them by the spectroscopic method, which is known as the atomic absorption spectroscopy method. That means the light is being absorbed, and then the spectroscope or the spectrograph can be produced, and on the basis of that we can understand their presence, or we can detect their presence. Why potassium and cesium are used in the photoelectric cell? Let us understand. When potassium and cesium are irradiated with the light energy absorbed may be sufficient to make an atom lose electron. This property makes cesium and potassium to make photoelectric cells. So please remember, my dear students, that these elements, potassium and cesium, just by falling the light on them, they can lose the electron, and that is why they are used to make the photoelectric or photovoltaic cells, my dear students. Let's move and understand about the chemical properties of these elements. Let's study about the chemical properties. The alkali metals are highly reactive due to their large size and low ionization energy or low ionization enthalpy. The reactivity of these metals increases down the group. So they have low value of ionization energy, and that is why they can easily lose electron, and that is why they can react well. And even if you go down the group, the reactivity increases. Reactivity towards air. How do these elements react with the air? Let us try to understand. The alkali metals tarnish in the dry air due to the formation of their oxides, which in turn react with the moisture to form hydroxides. So these, when they react with air or oxygen present into it, they form oxides, and these oxides, when they react with the moisture present in the air, they turn out to be hydroxides. These oxides and hydroxides are generally basic in nature, and that is why they are known as the alkali metals. They burn vigorously in or they means alkali metals burns vigorously in the oxygen, forming oxygen and forms the oxides. Lithium forms lithium oxide Li2O. Please remember, sodium forms peroxide Na2O2, where the other metals form the superoxides like KO2, CSO2, and RbO2. In the chapter, my dear students, redox reaction, we have seen that oxygen can be found into three different oxidation state. One is known as the O minus 2, which is known as oxide. The another one is O minus 1, which is known as the peroxide. And the third one is O2 minus 1, which is known as the superoxide. So you can see that potassium, cesium and rubidium form the superoxide. Sodium majorly form the peroxide, whereas lithium majorly form the oxides. These are the major oxides they form actually. They can even form the other forms of oxide simultaneously, but majorly they form these kind of oxides. The superoxides ion, that is O2 minus 1, is stable only in the presence of large cations such as potassium, rubidium and cesium, and that is why they form the superoxide, whereas lithium and sodium generally do not form the superoxide in the major quantity. We can understand the reactions. For lithium plus O2, it gives 2Li2O, which is an oxide. 2 sodium plus O2, that gives Na2O2, which is a peroxide. But if we take potassium, rubidium and cesium, so if we just write M plus O2, that gives MO2, that is potassium superoxide, rubidium superoxide and cesium superoxide, my dear students. So this is how it's easy for you to understand that going down the group, the atomic size increases, and at the atomic size increases, the bigger uh, uh, the bigger ions, they accommodate the bigger superoxide ion, and that is why they form the superoxides. In all these oxides, the oxidation state of alkali metal is always plus one. Please remember that all these oxides, the oxidation state of alkali metal is always plus one, and it is a permanent oxidation state which does not change in any of the compound of the alkali metals. Lithium shows exceptional behavior in reacting directly with the nitrogen of air to form Li3N. So lithium forms the lithium nitride Li3N as well. But the other element of this group, they generally do not directly react with the air or do not directly react with the nitrogen present in the air to form their nitrides. Because of their high reactivity towards air and water, alkali metals are normally kept in kerosene. Please remember that these metals are stored into the kerosenes, and as these metals are stored into the kerosene, why are these metals are stored into the kerosene? Because these metals are highly reactive, and they react with the moisture and oxygen present into the atmosphere, and that is why they prefer to or and that is why they are preferred to be stored into the kerosene, that is does not cause any accident, because they even violently react with the moisture and oxygen. What is the oxidation state of potassium in KO2? So the superoxide species is represented as O2. Since the compound is neutral, therefore the oxidation state of potassium is plus 1. So please remember that the alkali metals always shows the +1 oxidation state. All the alkali metals show always +1 oxidation state. Now, my dear students, we want to study about the reactivity towards water. Let us see how how these elements reacts with the water. The alkali metals reacts with water to form hydroxides and dihydrogen. So when alkali metal reacts with water, it forms the M plus, 2M plus and 2OH minus, which combinedly gives us the hydroxide, and they also produce the hydrogen gas. Here M represents the alkali metal. So M means alkali metal. That is what we need to know about. Uh, it may be noted that although lithium has most negative electrode potential value, please, this is the sign for the electrode potential value. Uh, it may be noted that although lithium has most negative electrode potential value, it reacts with water. Its reaction with water is less vigorous than that of the sodium, which has the least negative electrode potential value among the alkali metals. So, my dear students, here we get a new information that if you are asked about the electrode potential values, you should know that the electrode potential value of lithium is the most negative, and that is why lithium is a very good reducing agent or the best reducing agent. Among all these alkali metals, the electrode potential value of lithium is the most negative, and most the electrode potential value for sodium is the least negative. That means sodium is the
Mummy.
is, sodium is the most least reducing element among all these alkali metals, whereas lithium is the best reducing agent among all these elements. So please remember that reducing property we can determine using the value. This value is known as the electrode potential value. The more negative the value of the electrode potential, the better the element as a metal, or better the reducing property of that particular metal. This is the important point. Please remember. Let's move forward. This behavior of lithium is attributed to its small size and very high hydration energy. Other metals of the group react explosively with the water. So, apart from the lithium, all the elements of alkaline earth metal, they generally reacts very vigorously with the water, and they may cause accident, and that is why they are stored under kerosene or some other oils. They also react with the proton donors such as alcohol, gaseous ammonia, and alkynes. Please remember that these alkali metals, they react with the proton donors such as alcohol. They even react with the gaseous ammonia, and they even react with the alkynes. My dear students, I would like to tell you that if you have suppose sodium, and if it is allowed to react with CH triple bond CH, it produces the compound NaC2H2. So this kind of the amides, or you can say the this kind of the compounds are also formed by the sodium, which is known as the sodium ethynide. So this sodium ethynide is possible in case of the sodium, but lithium does not form this kind of ethanides. I hope, my dear students, you understand it well. So this is how, my dear students, we understand about the reactivity towards the water. My dear students, in the next period, we will study about the reactivity towards hydrogen and the other reactivities of these elements. I hope, my dear students, you have enjoyed your class. And if you have any doubt, you can ask me now. Okay,
Yes,
then,
sir.
my dear students, have a nice time.